Right now, you are made of matter. Every atom in your body, every star in the night sky, every planet in every galaxy, across the entire observable universe, all of it is matter. But the universe made something else at the very beginning, an equal amount of its opposite, a mirror substance so powerful that 1 single gram of it, meeting 1 single gram of you, would release the energy of 23 fully fueled space shuttles in a single instant. Scientists call it antimatter, and it is simultaneously the most perfect fuel ever conceived by physics, capable of carrying a spacecraft to the nearest star in a single human lifetime, and the most inaccessible substance that has ever existed. The universe made it in equal amounts. Then it nearly erased all of it. We have managed to trap 15,000 atoms. We need grams. The gap between those two numbers is not just an engineering problem. It is one of the deepest unsolved mysteries in all of science. And buried inside that mystery is the answer to why you exist at all. This is the engine that comes closer to breaking the speed of light than anything else physics permits. And this is the story of why the universe made it almost impossible to build. If this video sparked even one new thought about the universe, a like costs nothing, but helps everything for a small team trying to reach more curious minds. In 3, 2, 1, liftoff. Start with a number. Not because numbers are the best way to feel something, but because this particular number is so large, so absolute, so far beyond anything in ordinary human experience, that it stops being a number and starts being a statement about the nature of reality itself. 9 times 10 to the 16th joules per kilogram. Write that out in full, and it looks like this: 90 quadrillion joules released from every single kilogram of fuel consumed. That is the energy density of antimatter annihilation. That is what happens when matter meets its mirror twin. That is the number that makes physicists go quiet for a moment before they keep talking, because even people who have spent their entire careers working with the mathematics of it still feel the weight of it when they sit with it long enough. To understand what that number means in practice, you have to build a ladder. You have to start from the ground and climb, rung by rung, through everything humanity has ever used to move through space, and watch how each step upward looks increasingly small compared to the one above it, until you reach the top and realize the thing waiting there is in a category of its own. The bottom rung is where we live right now: chemical propulsion. The burning of hydrogen and oxygen, or kerosene and liquid oxygen, the same fundamental process that lifted Apollo astronauts off the surface of the moon and that currently powers the most capable rockets on Earth. Chemical combustion releases energy because the atoms in fuel molecules rearrange themselves into lower energy configurations, releasing heat and pressure as they go. It is fast. It is violent. It produces enough thrust to escape Earth's gravity well. And the energy density of the best chemical propellants, liquid hydrogen burned with liquid oxygen, sits at approximately 16 megajoules per kilogram. 16 million joules. That sounds enormous, until you learn what comes next. Nuclear fission tears atomic nuclei apart. When a heavy nucleus like uranium or plutonium splits into smaller fragments, the fragments weigh slightly less in total than the original nucleus did. That missing mass converts directly into energy, following Einstein's most famous equation. Energy equals mass times the speed of light squared. The energy released per kilogram of fissile material in a practical fission reaction reaches approximately 82 terajoules. That is 82 trillion joules per kilogram. More than 5 million times the energy density of chemical combustion from the same mass of fuel. That leap from chemical to fission is already staggering. It is the difference between the fire in a campfire and the fire in a star, and yet nuclear fission is not the top of the ladder. The next rung up is nuclear fusion, the process that powers the sun. When light nuclei, hydrogen isotopes like deuterium and tritium, fuse together to form helium, the resulting product again weighs slightly less than the ingredients. Again, that mass difference converts into energy. The energy density of a practical deuterium-tritium fusion reaction sits at approximately 339 terajoules per kilogram, roughly 4 times the energy density of fission, and somewhere in the neighborhood of 20 million times better than chemical combustion. Fusion is the dream that humanity has been chasing for 70 years. It is clean, abundant, and powerful enough to transform civilization's relationship with energy. And yet when you place fusion on the ladder and look at what sits above it, you realize fusion is not even the penultimate step. Antimatter annihilation sits above fusion by a factor of approximately 265. Not 265% better. 265 times better per kilogram. When a proton meets an antiproton and they annihilate, or when a positron meets an electron and they annihilate, 100% of the combined mass of both particles converts into energy. Every single bit of it. No waste products made of leftover matter. No heat dissipated into a reaction vessel. No partially converted fuel carried along as dead weight. The conversion is total, and it proceeds at the absolute maximum rate permitted by physics. That is what makes the number 90 quadrillion joules per kilogram so different from every number below it on the ladder. Every other energy source on that ladder is, at its core, rearranging matter in some way, whether chemically, nuclearly, or thermally. Antimatter annihilation does not rearrange matter. It eliminates it. Both the matter and the antimatter cease to exist as matter entirely, replaced by pure energy radiating outward at the speed of light in the form of gamma rays and secondary particles. This is not a more efficient version of combustion. It is a fundamentally different category of physical event. 1 gram of antimatter meeting 1 gram of ordinary matter releases approximately 1.8 times 10 to the 14th joules of energy. To give that number a texture, it is the equivalent energy of 23 fully fueled space shuttle external tanks. From 1 gram of fuel plus 1 gram of propellant, a space shuttle external tank holds approximately 730,000 kilograms of liquid hydrogen and liquid oxygen. 23 of those tanks, combined, carry approximately 16.8 million kilograms of propellant. And 1 gram of antimatter meeting 1 gram of matter releases energy equivalent to burning all of it simultaneously, not approximately, not roughly, with perfect efficiency, in a fraction of a second, from 2 grams total. If you could power a car with antimatter annihilation, a single sugar cube-sized amount of antimatter would fuel that car for millions of years of continuous driving, not an exaggerated approximation, a straightforward calculation from the energy density. Now, apply that to space travel. The problem with reaching the stars is not motivation. It is not imagination. It is not political will or funding. It is physics, specifically the physics of how much energy it takes to cover interstellar distances in any time frame that a human being or even a human civilization could consider meaningful. Proxima Centauri, the nearest star to our Sun, sits 4.24 light-years away. 1 light-year is approximately 9.5 trillion kilometers. Proxima Centauri is therefore approximately 40 trillion kilometers from Earth. Voyager 1, the most distant human-made object ever launched, has been traveling through space for more than 4 decades and is currently somewhere around 23 to 24 billion kilometers from Earth. At Voyager's speed, reaching Proxima Centauri would take over 80,000 years. 80,000 years. Modern human civilization, as we generally define it, is roughly 12,000 years old. The ancient Egyptians built the pyramids about 4,500 years ago. The time it would take Voyager to reach the nearest star is longer than all of recorded human history multiplied by 6 or 7. This is the core problem of interstellar travel. It is not about ambition. It is about the brutal arithmetic of distance and speed. To make interstellar travel a project that a civilization could realistically undertake, a spacecraft needs to travel at some meaningful fraction of the speed of light, not necessarily all of it. Even 1% of light speed would get you to Proxima Centauri in about 430 years. 10% of light speed gets you there in about 42 years. 30% gets you there in approximately 14 years. And here is where the antimatter ladder pays off in the most direct possible terms. Research published in the International Journal of Thermofluids in early 2025 by scientists Sorsan Ammar, Omaira, and Abdel Hamid Murad at United Arab Emirates University confirmed what propulsion theorists have been calculating for decades. Antimatter propulsion, under the right engine architecture, could accelerate a spacecraft to velocities approaching 30 to 40% of the speed of light, not in theory as a loose aspiration, but as a calculated output of antimatter annihilation physics applied to specific engine designs. At 30% of light speed, a crewed mission to Alpha Centauri, the nearest star system, at 4.3 light-years would take approximately 14 years. A round trip would take about 28 years. Not mythological, not the stuff of science fiction, requiring suspended animation across geological timescales. 28 years within the span of a single human life. That is what 90 quadrillion joules per kilogram means when you translate it into human stakes. It means the stars are not permanently out of reach. It means interstellar travel is a physics problem with a physical solution. It means the gap between here and there is bridgeable, not by dreaming, but by engineering. The question that immediately follows is obvious and necessary. If the physics is real, if the energy is real, if the numbers all work out this cleanly, then what is antimatter exactly, and where do we get it? Both questions require you to go back to a single extraordinary moment in the history of physics, the year 1928, and a 26-year-old British physicist named Paul Adrian Maurice Dirac. Dirac was attempting to do something that had never been done before: write an equation that correctly described the behavior of the electron while simultaneously satisfying both the rules of quantum mechanics and the rules of Einstein's special theory of relativity. The existing quantum theory of electrons worked reasonably well at low speeds, but it broke down under relativistic conditions, when electrons moved fast enough that their behavior was significantly affected by the distortions of space and time. Dirac wanted one equation that worked everywhere, at all speeds, under all conditions. He found it. The equation he produced, now called the Dirac equation, was one of the most mathematically beautiful structures in the history of physics, and it worked. It correctly predicted the behavior of electrons under relativistic conditions. It explained the electron's intrinsic spin, a property that had been measured but never derived from first principles. It was a complete, self-consistent, and experimentally validated triumph, but the equation had a problem, or rather, an unexpected result that looked like a problem but turned out to be something else entirely. When Dirac solved his equation for the energy states of an electron, the mathematics produced two sets of solutions. One set described electrons with positive energy, which made immediate physical sense. The other set described electrons with negative energy, which made no sense at all under any existing physical framework. Negative energy meant a particle that would keep falling into lower and lower energy states forever, releasing infinite energy as it went. The universe would be instantly unstable. Obviously, that was not happening. Dirac tried several interpretations. He initially proposed that all the negative energy states were already filled with electrons, forming an invisible sea of occupied states that real electrons could not fall into, because quantum mechanics forbids two electrons from occupying the same state simultaneously. He called this the Dirac sea. It was a creative and technically defensible solution, but it implied that a hole in the Dirac sea, a missing electron from among the infinite sea of negative energy states, would behave like a positively charged electron. A particle with the mass of an electron but positive charge. In 1932, 4 years after Dirac published his equation, the American physicist Carl David Anderson was studying cosmic rays using a device called a cloud chamber, which made the paths of charged particles visible as trails of condensed vapor. He placed the chamber in a strong magnetic field. A magnetic field curves the path of a charged particle, curving it one way for negative charges and the other way for positive charges. The radius of the curve reveals the particle's momentum, and therefore its mass. Anderson observed a particle that curved exactly the wrong way for an electron, but with exactly the right radius for a particle with the mass of an electron. The curvature was unambiguous. The mass was unambiguous. He was looking at a positively charged particle with the same mass as an electron. He called it the positron and published his discovery in the journal Science in September of that year. Dirac's equation had predicted it. Anderson had found it. The universe contained not just particles, but antiparticles. The positron is the antiparticle of the electron. It has exactly the same mass as an electron. It has exactly the same spin, but its electric charge is positive instead of negative. Everything about it is a precise mirror image of the electron, reversed in the specific quantum properties that can be reversed. The electron and the positron are a matched pair built into the mathematics of quantum field theory with the same unavoidable necessity as left hands and right hands in a universe with bilateral symmetry. This was not a peculiarity of electrons. As the mathematics of quantum field theory developed through the 1940s, 50s, and beyond, it became clear that every fundamental particle in the universe has a corresponding antiparticle. The proton has the antiproton, identical in mass, but with negative electric charge instead of positive. The neutron has the antineutron, electrically neutral, like the neutron, but with its internal quark structure reversed in a specific quantum sense. The neutrino has the antineutrino. Even particles like the photon, which carry no charge, technically have antiparticles, though in the photon's specific case, the antiparticle is identical to the particle itself. This is not a quirk of human notation or an artifact of the way we choose to describe physics. It is a deep structural feature of reality, embedded in a fundamental symmetry of nature called CPT symmetry, the combined symmetry of charge conjugation, parity transformation, and time reversal. CPT symmetry states that the laws of physics must remain identical if you simultaneously reverse all charges, mirror all spatial coordinates, and reverse the direction of time. This symmetry is one of the most precisely tested principles in all of science, and it implies with mathematical certainty that every particle must have an antiparticle twin with reverse charges and quantum numbers. Antimatter is therefore not exotic in the sense of being outside physics. It is a required feature of physics. Its existence is not an accident or an anomaly. The universe is built in a way that demands it. Now comes the annihilation itself, because this is the engine at the heart of everything that follows. When a particle meets its corresponding antiparticle, they do not simply collide and bounce away. They annihilate. The word is precise and not hyperbolic. Both particles cease to exist entirely as matter. The combined mass of the two particles, every single gram of it, converts into energy according to Einstein's equation, E equals mc squared. The speed of light squared is approximately 9 times 10 to the 16th meters squared per second squared, which is an enormous multiplier even on small masses. A single proton-antiproton pair, each weighing about 1.67 times 10 to the negative 27th kilograms, releases approximately 3 times 10 to the negative 10th joules of energy when they annihilate. That sounds tiny until you multiply by Avogadro's number of pairs, arriving at the macroscopic quantities where the 90 quadrillion joules per kilogram figure lies. The products of proton-antiproton annihilation are not simple. When a proton and an antiproton meet, they do not instantly vanish into 2 photons the way an electron and a positron do. Instead, the annihilation proceeds through the strong nuclear force, producing a spray of particles called pions. Proton-antiproton annihilation typically produces, on average, around 5 pions per event, a mix of positively charged pions, negatively charged pions, and neutral pions. The neutral pions decay almost instantly, within approximately 8.4 times 10 to the negative 17th seconds, into pairs of high-energy gamma-ray photons. The charged pions live longer, for approximately 26 nanoseconds on average before decaying into muons and neutrinos, and the muons themselves carry a large fraction of the original annihilation energy as kinetic energy of relativistic charged particles. This pion cascade is actually critically important for propulsion. Gamma rays, while they carry energy, are notoriously difficult to redirect into thrust because they pass through almost any material without interaction. But charged pions and their muon products carry momentum as relativistic charged particles, which means a magnetic field can deflect them. A sufficiently strong magnetic nozzle can redirect the charged products of proton-antiproton annihilation into a directed beam, and a directed beam of relativistic particles is thrust. This is the physical mechanism underlying the most powerful antimatter engine designs. Not just the energy of annihilation, but the specific character of what annihilation produces: charged, relativistic, magnetically steerable particles that makes it something more than just an energy source. It is an energy source whose exhaust products are naturally adapted to the physics of propulsion. Electron-positron annihilation follows a different pathway. When an electron meets a positron, the annihilation is simpler. Both particles vanish and two gamma-ray photons emerge, each carrying exactly half of the total energy, traveling in opposite directions to conserve momentum. These photons carry no charge, so magnetic fields cannot redirect them. For propulsion purposes, electron-positron annihilation is harder to harness directly as thrust than proton-antiproton annihilation, though the energy released is equally complete and equally real. The specific impulse achievable from antimatter propulsion is the figure that propulsion engineers care about most, because specific impulse, measured in seconds, tells you how efficiently a propellant system turns fuel mass into velocity change. Chemical rockets achieve specific impulse values of roughly 400 to 450 seconds for the best hydrogen-oxygen engines. Ion drives, which are used on missions like the Dawn spacecraft and are considered extremely efficient for their power level, reach specific impulse values of around 3,000 to 10,000 seconds. Nuclear thermal rockets, which heat propellant by passing it through a nuclear reactor, could potentially reach specific impulse values of around 900 seconds. The beam core antimatter engine, the most advanced architecture on the theoretical drawing board, achieves specific impulse values in the range of approximately 1 million seconds. Not a factor of 2 or 3 better than chemical rockets, not an order of magnitude better, roughly 2,000 times better than the best hydrogen-oxygen engines ever built. That specific impulse advantage is what makes the difference between a spacecraft that requires a planet's worth of fuel to reach the nearest star and one that requires grams. The mass ratio calculations for antimatter propulsion, when the specific impulse is in the range of 1 million seconds, are not just favorable, they are transformative. A spacecraft could carry a relatively modest mass of antimatter fuel and still achieve the acceleration profile needed for a transit to Proxima Centauri in a human lifetime. The physics is real. The mathematics checks out. The energy is real, verified through particle accelerator experiments in which proton-antiproton annihilations have been observed, measured, and characterized thousands of times per second in facilities like CERN and Fermilab. There is no theoretical obstacle preventing an antimatter engine from working. What there is instead is a gap between the physics and the engineering so wide that crossing it would represent one of the largest technological achievements in human history. And understanding that gap requires understanding something about where antimatter actually comes from and why it is so ferociously difficult to obtain. The universe made it once, in the first moments after the Big Bang, in quantities vast enough to fill the cosmos. Something happened to almost all of it, and we will return to that mystery in full in Part 4. But the trace amounts of antimatter that exist in the observable universe today are not idle or invisible. They are produced continuously in small amounts by high-energy cosmic rays slamming into the upper atmosphere and producing particle-antiparticle pairs. They are produced in medical imaging facilities every day, where cyclotrons create positrons that are then used in positron emission tomography scanners to generate detailed three-dimensional images of the human body's metabolic activity. Millions of people alive today have had antimatter positrons injected into their bloodstream for a medical scan, and the positrons annihilated with electrons in their tissues within a few millimeters of where they were created, producing the gamma-ray signals that the scanner detects. And they are produced with extraordinary precision and difficulty at particle accelerators like CERN's antiproton decelerator in Geneva, Switzerland, the most sophisticated antimatter production facility on Earth. The anti-proton decelerator was not built to make rocket fuel. It was built to answer fundamental questions about the nature of matter and antimatter, about symmetry and the deep structure of physical law. But the quantities it produces and the methods it uses represent the current state of the art in human antimatter technology. What CERN currently produces, at the frontier of global capability, is approximately 10 nanograms of antiprotons per year. 10 nanograms. A nanogram is 1/billionth of a gram. 10 nanograms is 10 billionths of a gram. An eyelash weighs approximately 60 to 90 micrograms, which is somewhere between 6,000 and 9,000 nanograms. The entire annual antiproton output of the most advanced antimatter facility in the world would weigh about 0.1% of a single human eyelash. And yet, even that impossibly small amount costs millions of dollars per year to produce, because making antiprotons requires an enormous infrastructure of particle accelerators, magnets, detection equipment, and cryogenic cooling systems, consuming vast amounts of electrical power. The arithmetic is brutal. Scaling up to produce 1 gram of antimatter using current technology would require approximately 25 million kilowatt-hours of energy, enough to power a small city for a full year, and would cost somewhere between $25 billion and $62.5 trillion, depending on the production efficiency assumptions used. But the physics works. The energy is real. The speeds are achievable in principle. The question of how to bridge that gap between nanograms and grams, between a cloud chamber and an engine, is where the story goes next. And the answer begins with understanding the specific machines that propulsion engineers have designed to harness antimatter's power, because those designs reveal precisely how and why every gram of antimatter matters more than almost anything else humanity could conceivably manufacture. The ladder has been climbed, the number has been felt, the particle has been named and discovered, and its annihilation traced through the cascade of pions and gamma rays that physics produces when matter and antimatter meet. The stars are 14 years away, in principle, at the energies antimatter can provide. What stands between the principle and the practice is the engine itself, and that story is more intricate and more elegant than most people ever get to hear. There is a particular kind of engineering drawing that exists in the files of NASA research centers, in university aerospace departments, and in the pages of peer-reviewed propulsion journals that most people will never see. These drawings look, at first glance, like something a physicist might sketch on a whiteboard during an afternoon conversation that got ambitious. They have labels like magnetic nozzle and pion collimation zone and annihilation chamber. They have specific impulse figures annotated in the margins. They have mass ratios calculated for target missions to Alpha Centauri or Proxima Centauri. They are drawn with the precision and care that serious engineering demands. They are blueprints for starships, not conceptual art, not science fiction concept designs. Engineering designs, grounded in verified physics, developed by credentialed propulsion scientists at institutions including NASA, Marshall Space Flight Center, Pennsylvania State University, and universities across Europe over a period of decades. The antimatter engine is not a dream that physicists have occasionally entertained at conferences. It is a design problem that has been worked on systematically, carefully, and with increasing technical depth for the better part of a century. Understanding the four classical antimatter propulsion architectures requires starting with a fundamental question. What do you actually do with the energy that antimatter releases? This is not a trivial question. The annihilation event produces energy in forms that are both incredibly powerful and surprisingly difficult to translate into directed thrust. Gamma rays, which carry roughly half the energy from proton-antiproton annihilation via neutral pion decay, travel at the speed of light and pass through almost any material without depositing significant energy. You cannot aim them with a physical nozzle the way you aim hot gas from a chemical engine. The other half of the energy emerges as charged pions, which are relativistic but short-lived, decaying into muons and neutrinos within a handful of nanoseconds in the frame of the spacecraft. The four engine architectures represent four different engineering solutions to this translation problem, each trading off specific impulse against thrust, engineering complexity against fuel efficiency, and near-term feasibility against maximum theoretical performance. The first and most conceptually straightforward is the solid core antimatter engine. The design logic here draws deliberately from nuclear thermal rocket concepts that were actually built and tested during the 1960s under the American program known as NERVA, Nuclear Engine for Rocket Vehicle Application. In a nuclear thermal rocket, a nuclear fission reactor heats a propellant, typically liquid hydrogen, by passing it through or around the reactor core. The heated hydrogen expands and exhausts through a nozzle, generating thrust. The specific impulse achievable with nuclear thermal rockets, around 800 to 900 seconds, is roughly double that of the best chemical engines. The solid core antimatter engine applies the same principle, but with antiprotons, rather than fission neutrons, as the energy source. Antiprotons are injected into or around a solid core material where they annihilate with the nuclei of the core's atoms. The energy released heats the solid material to extreme temperatures, and liquid hydrogen propellant is then pumped through channels in the core, heated to plasma temperatures by the antimatter heated structure, and expelled through a magnetic or physical nozzle to generate thrust. The specific impulse achievable with a solid core antimatter design sits in the range of approximately 1,000 to 2,000 seconds. That is meaningfully better than chemical combustion and comparable to or better than nuclear thermal rockets. But it is not the dramatic leap that antimatter's energy density seems to promise. The reason is thermodynamic. The solid core acts as an intermediary. The antimatter's energy heats the solid, and the solid heats the propellant, but the solid has a melting point and a vaporization temperature that caps how hot the propellant can get before the core itself is destroyed. The limiting factor is not antimatter. It is materials science. The hottest solid materials humans have ever manufactured begin melting somewhere around 3,000 to 4,000 Kelvin, which fundamentally limits the exhaust velocity and therefore the specific impulse of any solid core design, regardless of how energetic the fuel source is. Nevertheless, the solid core design has engineering advantages that more advanced architectures lack. It is conceptually simpler. It requires less exotic containment technology. The annihilation events occur inside a structured physical medium that can be engineered with familiar techniques, even if the temperatures and particle fluxes involved are extreme. For a near-term mission profile, not a journey to another star system, but perhaps an extremely fast transit of our own solar system, or an interstellar precursor mission to probe the region just beyond the heliopause, the solid core design represents a technically comprehensible starting point. The second architecture, the gas core antimatter engine, removes the solid material intermediary and allows the annihilation to take place in a gaseous or plasma medium. The operating principle is similar in broad strokes. Antiprotons annihilate within the working fluid, heated directly, and the heated fluid is exhausted for thrust. But because there is no solid material with a fixed melting point to limit the temperatures involved, the gas core design can operate at significantly higher temperatures. The working fluid, typically a mixture of hydrogen and whatever material the annihilation products interact with efficiently, can reach temperatures of tens of thousands of Kelvin. The specific impulse of a gas core antimatter engine sits in the range of approximately 10,000 to 50,000 seconds. This is a meaningful improvement over the solid core design, representing a factor of roughly 10 to 25 improvement. At these specific impulse values, the fuel efficiency becomes attractive enough that a spacecraft mission profile to the outer planets of our solar system or to relatively nearby interstellar targets begins to look substantially more feasible from a mass ratio perspective. The engineering challenges of the gas core design are considerable. Containing a high-temperature plasma that is also being continuously heated by annihilation events requires sophisticated magnetic confinement or other containment approaches. The annihilation chamber must somehow prevent the working fluid from simply exploding outward in all directions while still allowing controlled ejection through the nozzle. The antiprotons must be delivered into the reaction zone with sufficient precision to annihilate within the heated gas rather than on the walls of the containment structure. Because any antiproton that touches a solid wall of normal matter annihilates there, instead of in the working fluid, contributing heat in the wrong place and potentially damaging the structure. These are real engineering problems with no simple solutions. But they are, at least in principle, engineering problems rather than physics problems. There is no law of nature that forbids a gas core antimatter engine from working. There are only materials and precision and funding barriers standing between the design and the hardware. The third architecture represents a more significant departure from conventional propulsion concepts and pushes into territory that has no historical analog in human engineering. The plasma core antimatter engine operates at temperatures so extreme that neither solid materials nor simple gases can contain the working fluid in any conventional sense. At the temperatures achievable when antiproton annihilation is allowed to proceed with minimal thermodynamic intermediaries, temperatures ranging from hundreds of thousands to millions of Kelvin, any material in contact with the plasma would be instantly vaporized. The containment must therefore be entirely magnetic. In a plasma core design, a powerful magnetic field configuration, analogous in some ways to the magnetic confinement systems used in experimental fusion reactors, creates a region of space in which the annihilating plasma is confined. The antiprotons annihilate within this plasma, heating it to extreme temperatures. The plasma itself, being composed of ionized charged particles, is steerable by magnetic fields. A carefully shaped magnetic nozzle can accelerate the plasma out of the confinement region in a specific direction, generating thrust. The specific impulse achievable with plasma core antimatter designs rises into the range of approximately 100,000 to 500,000 seconds. This is the territory where interstellar mission profiles begin to look genuinely tractable from a fuel mass standpoint. The mass ratios required to reach 30% of light speed are demanding, but not astronomically so if the propellant can be managed as efficiently as plasma core designs suggest. The specific impulse advantage comes with a thrust penalty that matters for mission design. Higher specific impulse generally means lower thrust at the same power level, because you are getting more velocity per kilogram of propellant, but doing so more gradually. A plasma core antimatter engine would likely accelerate a spacecraft slowly by terrestrial standards, building velocity over months or years of continuous operation rather than in a brief explosive burn. 4. Interstellar missions. This is acceptable because the journey itself takes years regardless. The spacecraft can afford to spend the first year accelerating, but for missions within the solar system requiring rapid transit, the thrust level of a plasma core design might be more limiting. The fourth architecture is where the physics of antimatter reaches its theoretical peak performance, and where the engineering departs most dramatically from anything humanity has ever built. The beam core antimatter engine dispenses with propellant almost entirely. In the beam core design, protons and antiprotons are stored separately and brought together in a carefully controlled annihilation chamber. The charged pions produced by proton-antiproton annihilation, as described in Part 1, emerge from the annihilation event as relativistic particles with significant momentum. In a beam core engine, a magnetic nozzle structure is designed to collimate these charged pions, to take the spray of particles emerging from annihilation and redirect those traveling in roughly the desired direction into a coherent directed beam, while allowing the others to be lost or to serve as an energy source for other spacecraft systems. The directed beam of charged pions emerging from the magnetic nozzle is the exhaust. There is no additional propellant being heated and expelled. The exhaust is composed of the relativistic products of the annihilation reaction itself. These pions travel at a significant fraction of the speed of light, giving them an exhaust velocity far exceeding anything achievable with a heated propellant. The specific impulse of a beam core design, calculated from the effective exhaust velocity of the pion beam, sits in the range of approximately 1 million seconds. 1 million seconds of specific impulse. To put that in perspective using a physical comparison made only here, if specific impulse were a measure of altitude, chemical rockets would be standing at street level, ion drives would be at the rooftop of a skyscraper, and the beam core antimatter engine would be orbiting in low Earth orbit. The categories are not comparable. The beam core engine is not a more efficient version of anything that has come before it. It is a different kind of machine, operating in a different physical regime. The propellant mass requirements for a beam core antimatter spacecraft attempting a transit to the nearest star system are, relative to any other conceivable engine, modest. Calculations suggest that a spacecraft with a dry mass of a few hundred metric tons could potentially reach 30% of light speed while carrying a fuel load measured in tens of grams to a few kilograms of antimatter. The exact figures depend on mission profile, acceleration duration, and design specifics. But the key point is the scale. Kilograms of fuel, not millions of kilograms. Grams. In the most optimistic scenarios, the engineering challenges of the beam core design are severe and numerous. Magnetic nozzle structures strong enough to collimate relativistic pions would require magnetic field strengths far beyond any magnet currently in operation. The geometry of the nozzle must be designed to capture and redirect a significant fraction of the pion spray, which emerges in all directions from the annihilation event, not just the convenient direction. The structural materials of the spacecraft must withstand the radiation environment created by the annihilation events and by the pions themselves, which are energetic enough to damage materials at the nuclear level. The storage and delivery of antiprotons to the annihilation chamber must be accomplished with enough precision and throughput to sustain a continuous reaction. None of these challenges are impossible in principle. All of them are beyond current engineering capability by a margin that can be characterized honestly only as civilizational. Achieving beam core antimatter propulsion would require advances in superconducting magnet technology, radiation-hardened materials, cryogenic storage, particle delivery systems, and overall spacecraft integration that likely represent at minimum decades, and more probably centuries, of sustained engineering development. Between the idealized theoretical performance of the beam core and the acknowledged near-term impossibility of building one, there is a middle path that propulsion engineers have studied carefully, and that represents the most practically promising near-term direction for antimatter propulsion: the antimatter catalyzed fission-fusion hybrid engine. This design concept, studied in depth by researchers at NASA Marshall Space Flight Center and Pennsylvania State University, and analyzed in NASA technical reports since the late 1990s, offers a way to exploit antimatter's unique physics while requiring dramatically smaller amounts of the substance. The key insight is that antiprotons are extraordinarily good at triggering nuclear reactions in fissile and fusible materials. When an antiproton slows down and is captured by a heavy nucleus, it annihilates with one of the nucleus's constituent protons or neutrons in a process that releases enough energy and disruption to cause the heavy nucleus to fission. The antiproton acts not primarily as a fuel, but as a precision trigger. In the antimatter catalyzed fission-fusion hybrid, a tiny quantity of antiprotons, measured in micrograms rather than grams, is injected into a target of fissile material surrounded by fusible material. The antiprotons trigger fission in the fissile target. The fission releases enormous energy and a burst of neutrons and radiation that compresses and heats the surrounding fusible material to the conditions needed for thermonuclear fusion. The combined fission-fusion reaction releases energy at a scale thousands of times larger than the antiproton input alone could provide. The antiprotons are the spark, not the fuel. The fissile and fusible materials do most of the energy work. This architecture is transformative for a specific reason. It changes the antimatter requirement for a practical propulsion system from grams or kilograms down to micrograms. A microgram is 1/1,000,000th of a gram. CERN currently produces about 10 nanograms of antiprotons per year, which is 10 millionths of a gram, already within an order of magnitude of the microgram scale for the most modest mission concepts. NASA analyses have suggested that a dedicated antiproton production facility, distinct from a basic research accelerator and optimized specifically for production efficiency, could potentially produce microgram quantities annually, with an investment on the order of $15 billion in infrastructure. $15 billion is not a small number, but it is a number that human civilization has spent on individual scientific projects before. The James Webb Space Telescope cost approximately $10 billion. The Large Hadron Collider at CERN cost approximately $5 billion to build, plus ongoing operational costs. A dedicated antimatter production facility at the scale needed for antimatter catalyzed propulsion is expensive, but it is within the range of what a committed international scientific program could contemplate. NASA technical analyses have assessed that antimatter catalyzed fission-fusion systems could feasibly support missions described as interstellar precursor missions and what the reports term omniplanetary spaceflight, transit to any destination in the solar system with antimatter costs ranging up to approximately $60 million per mission at projected near-term production capacities after infrastructure investment per mission for access to the entire solar system. The economics are not yet competitive with conventional rockets for nearby destinations, but for missions to the outer solar system, for Uranus, Neptune, the Kuiper Belt, or the heliopause, where travel times with conventional propulsion are measured in decades, an antimatter catalyzed engine that could drastically reduce those transit times represents a qualitatively different capability. 1 gram of antihydrogen, the CERN technical team has noted in their own communications, could ideally power 23 space shuttles. 1 gram, combined with 1 gram of normal hydrogen in an annihilation reaction, releases energy equivalent to 23 space shuttle external tanks of chemical propellant. The antimatter catalyzed design uses far less than a gram for a mission, but it unlocks the energy of far more conventional nuclear material than the antimatter alone could provide. The leverage ratio between antiproton input and total energy output is part of what makes the architecture attractive to practical mission planners. The specific impulse of an antimatter catalyzed fission-fusion hybrid sits somewhere between the modest performance of the solid core design and the extreme performance of the beam core, depending on specifics. Estimates typically range from approximately 13,000 to approximately 100,000 seconds, varying with the mix of fission and fusion products and the efficiency of nozzle design. This is firmly in the range where missions to the outer planets in months rather than years become calculable, and where interstellar precursor probes to the distances of a few light years become a topic of genuine mission design rather than pure speculation. The Positron Dynamics Company, a space startup led by Ryan Weed, has been developing an approach based specifically on positrons, the antiparticles of electrons, rather than antiprotons. Positrons are significantly easier to produce than antiprotons because they can be generated in substantial quantities by certain radioactive isotopes and by compact cyclotrons of the type already operating in medical imaging facilities around the world. The positron dynamics engine concept uses a moderated positron beam to catalyze the nuclear reactions in a propellant medium, functioning, in some ways, analogously to the antimatter catalyzed hybrid concept, but relying on positrons rather than antiprotons. The company claims potential specific impulse values up to approximately 1,000 times better than current ion drives, which would place their system in the range of tens of millions of seconds under idealized assumptions. These figures are not yet independently confirmed through the kind of rigorous peer-reviewed engineering validation that the more established engine architectures have undergone, and should be understood as preliminary claims from a development stage company. But the underlying physics of positron-catalyzed nuclear reactions is real, and the concept represents an active area of private sector interest in the antimatter propulsion space. What these four architectures and the catalytic hybrid designs share is a common physical foundation, the annihilation event and the energy it releases. They differ in how they capture that energy, how they translate it into directed thrust, and how much antimatter they require to perform a given mission. The solid core trades performance for simplicity. The gas core trades engineering complexity for improved specific impulse. The plasma core pushes into magnetic confinement territory for another order of magnitude of improvement. The beam core achieves the theoretical ceiling at the cost of engineering challenges that border on the civilizational. The catalytic hybrid inserts itself as the pragmatic middle path, requiring the least antimatter while still delivering performance far beyond any conventional engine. Each design exists not as speculation, but as a system of equations and technical documents. Mass ratios have been calculated, mission profiles have been sketched, thrust levels have been estimated, the propellant requirements for specific missions have been computed with genuine engineering rigor. The drawings are real, the physics behind them is real, and the gap between the drawings and a functioning engine is real as well. That gap is not primarily a matter of understanding the physics better. The physics is understood well enough to design the engines on paper. The gap is a matter of material, specifically the matter of producing, capturing, and containing the one substance that all of these engines require in quantities ranging from micrograms to grams. That substance, antimatter, is at once the most energetic material in the known universe and the most elusive thing humanity has ever attempted to manufacture. The scale of the production problem and the extraordinary recent breakthroughs that are beginning to chip away at it, and the containment paradox that makes storing the perfect fuel its own civilizational engineering challenge. All of that waits in the next chapter of this story, where the physics of the perfect engine meets the brutal arithmetic of what it actually takes to fill its tanks. Begin with a practical question, not a philosophical one, not a theoretical one, but the kind of question an engineer would write at the top of a whiteboard before a long meeting. How do you actually make antimatter? The answer requires understanding what CERN's antiproton decelerator does, in physical terms, step by step, because the process itself reveals why the production problem is not simply a funding gap or an engineering bottleneck, but a consequence of the deepest thermodynamic constraints in nature. The antiproton decelerator sits in a building on the CERN campus in Meyrin, Switzerland, adjacent to the sprawling underground ring of the Large Hadron Collider, but operating independently of it, focused on a completely different set of experimental goals. It was built not to smash particles at the highest possible energies, but to do something in some ways more technically demanding, to slow down antiprotons to the point where they can be captured, studied, and used in precision experiments. Slowing down antimatter is difficult for reasons that will become obvious in a moment. The process begins with a proton beam, a conventional particle accelerator, specifically the proton synchrotron at CERN, accelerates protons to an energy of 26 giga-electron volts and slams them into a fixed metal target, typically made of iridium. The collision energy is high enough to produce matter-antimatter pairs directly from the kinetic energy of the collision. Through the inverse of Einstein's equation, energy converts into mass, appearing as pairs of particles and their corresponding antiparticles. Among the particles produced in this spray of collision debris are antiprotons. The antiprotons emerge traveling at relativistic speeds in a range of directions, mixed in with a large number of ordinary particles produced in the same collision. The antiprotons are separated from the ordinary collision products using magnetic fields, which curve positive and negative charges in opposite directions, allowing the antiprotons, which are negatively charged, to be directed into a separate beam path, while most of the positively charged particles are discarded. This selected antiproton beam is then fed into the antiproton decelerator, a ring-shaped storage device with a circumference of approximately 182 meters, where a series of sophisticated techniques decelerate the antiprotons from their initial high energies down to a few mega-electron volts, a fraction of 1% of the speed of light, slow enough to be trapped and used in experiments. The deceleration itself requires what physicists call stochastic cooling and electron cooling, techniques that reduce the spread of momenta among the antiprotons in the beam, making them travel together in a tight, controllable group rather than spreading out chaotically. The cooling does not slow the antiprotons by letting them lose energy through friction, the way cooling works in everyday experience. It works by detecting the statistical spread of particle momenta in the beam and applying corrective electromagnetic kicks to reduce that spread, cycle after cycle, until the beam is cold enough, tight enough, in phase space to be usefully decelerated. The engineering required to accomplish this in real time for particles traveling at nearly the speed of light and lasting only as long as they are kept away from normal matter is extraordinary. At the end of this process, the antiproton decelerator delivers a usable beam of slow antiprotons to the experimental zone where various physics experiments, including the Alpha Collaboration's anti-hydrogen trapping apparatus, are situated. The annual output of this entire infrastructure, including the primary accelerator that makes the antiprotons, the deceleration ring, the cooling systems, and all the supporting equipment, is approximately 10 nanograms of antiprotons. 10 nanograms. The number appeared in Part 1 as a statement of magnitude. Here, it is worth examining the mechanism behind it to understand why increasing the output is not a matter of simply building a bigger version of the same machine. The fundamental constraint is thermodynamic. To produce an antiproton, you must invest energy at least equal to the rest mass energy of a proton-antiproton pair, which is approximately 1.88 giga-electron volts total. That is the absolute physical minimum, the floor set by Einstein's equation itself. You cannot create a proton-antiproton pair from less energy than their combined rest mass. In practice, the efficiency of converting the accelerated proton beam's kinetic energy into antiprotons through the collision process is extraordinarily low. For every million protons that strike the iridium target, only a handful of antiprotons are produced with momenta and directions suitable for collection and use. Most of the energy in the beam heats the target, produces pions that immediately decay, or generates other particles that are not useful. The effective energy efficiency of current antimatter production, from electrical input to useful antiproton output, is approximately 10 to the negative 9th power, meaning that for every joule of antimatter energy produced, roughly 1 billion joules of electrical energy must be consumed. This is not a failure of engineering design. It is a consequence of the physical process being used. Creating matter-antimatter pairs from energetic collisions is inherently inefficient because the kinetic energy of the beam must exceed the pair production threshold, and most of the energy goes into secondary processes that are thermodynamically unavoidable in high-energy proton collisions with fixed targets. No amount of engineering cleverness can circumvent the conservation of energy, and the ratio between electrical energy invested and antimatter energy produced is bounded by fundamental physics. Extrapolating this efficiency to the gram scale reveals the production problem in its starkest form. Producing 1 gram of antimatter at current efficiency would require approximately 25 million kilowatt-hours of electrical energy. The global average cost of industrial electricity sits somewhere around 5 to 10 cents per kilowatt-hour. At 5 cents per kilowatt-hour, the energy cost alone for 1 gram of antimatter would be approximately $1.25 million. That sounds manageable until you factor in that the current global infrastructure for antiproton production operates at its maximum practical capacity to deliver 10 nanograms per year. Scaling to gram quantities is not a matter of multiplying the electrical bill by 100 million. It requires building 100 million times more antiproton production capacity, which means 100 million times more accelerator infrastructure, 100 million times more target material handling, 100 million times more beam collection and cooling capacity. NASA technical documents have estimated the cost of 1 gram of antiprotons produced with current technology at approximately $62.5 trillion. That figure reflects not just the electricity cost, but the full cost of the infrastructure required to produce that gram over a practical time period. $62.5 trillion is approximately twice the annual gross domestic product of the entire United States economy. For 1 gram of fuel, the most capable rocket engine humanity has ever seriously designed on paper requires tens of grams to kilograms of this substance for a mission to the nearest star. This is the production crisis in its quantitative form. It is not a gap that can be closed by spending more money on the current approach. The current approach is itself the problem, because it was designed for particle physics research, not fuel production. A dedicated antimatter factory, built specifically to maximize production efficiency rather than to serve the needs of collision experiments, would look very different from CERN's antiproton decelerator. Proposals for such facilities have been studied, and the numbers improve substantially. NASA Marshall Space Flight Center researchers have estimated that a dedicated antiproton production facility based on existing technology could be built for an investment of approximately $5 billion to $15 billion. Such a facility, designed from the ground up for production efficiency rather than research versatility, could potentially reduce the cost per gram of antiprotons to approximately $25 billion and increase annual production rates to microgram quantities, micrograms per year, from a dedicated $15 billion facility. That is still 6 orders of magnitude away from gram quantities per year, but it places antimatter catalyzed propulsion missions, which require only microgram to submilligram quantities of antiprotons, within the range of what an aggressive near-term program could consider. There is a second potential source of antimatter that does not require building accelerators at all, and it is one of the more intriguing candidate ideas in the propulsion research community, though it remains firmly in the candidate category rather than the confirmed solution category. Earth is continuously bathed in cosmic rays, high-energy particles, primarily protons, and heavier atomic nuclei, streaming in from throughout the galaxy and beyond. When these cosmic ray protons strike atoms in the upper atmosphere or the nuclei of gas molecules in the magnetosphere, they undergo collisions energetic enough to produce proton-antiproton pairs. The antiprotons produced in these collisions are mostly swept away into space, but some fraction of them are captured by Earth's magnetic field and trapped in a region of space called the inner Van Allen radiation belt. The Van Allen belts are zones of trapped, charged particles surrounding Earth, held in place by Earth's magnetic field lines. The inner belt, sitting between roughly 1,000 and 6,000 kilometers above Earth's surface, depending on latitude, contains primarily high-energy protons and electrons from cosmic ray interactions. In 2011, the Pamela satellite mission confirmed the presence of antiprotons in the inner Van Allen belt, trapped there by the same magnetic field physics that traps normal protons. The quantity is small. Estimates suggest a total antiproton population in the inner belt on the order of 160 nanocoulombs, which translates to an extremely small number of actual particles. But the antiprotons are continuously replenished by ongoing cosmic ray interactions. The proposal to harvest Van Allen belt antiprotons using magnetic scoops, spacecraft with superconducting magnetic field generators that would sweep through the belt and capture antiprotons the way a net sweeps through water, has been studied seriously enough to appear in NASA-funded research documents. Jupiter's much stronger magnetic field and its much larger magnetospheric volume would trap proportionally larger quantities of cosmic ray-produced antiprotons, potentially making Jovian antiproton harvesting a long-term candidate source. The engineering challenges of operating collection spacecraft in the intense radiation environment of the Van Allen belts, or the far more intense radiation environment of Jupiter's inner magnetosphere, are formidable, and the quantities collectible with any practically conceivable spacecraft design remain orders of magnitude below what even the antimatter catalyzed hybrid propulsion designs would require for a mission. The Van Allen antiproton source is not a solution to the production crisis. It is a data point demonstrating that the universe does create antimatter naturally and continuously in small quantities near Earth, and that cosmic ray physics provides a non-accelerator pathway to antiproton production in principle. Whether that pathway could ever be scaled to useful quantities for propulsion is a question that remains genuinely open, belonging in the candidate explanation category rather than the confirmed or even strong interpretation categories. But none of the production questions are the deepest engineering problem that antimatter propulsion faces. The deepest problem is containment, and it is worth sitting with the precise physical nature of the challenge for a moment before discussing how physicists have approached solving it. Consider what it means to store antimatter. The substance annihilates on contact with any normal matter, not with some matter, with all matter, every molecule of the container wall, every atom of any gas that might be present in the storage vessel, any photon at the right energy that might interact with the antimatter in a matter-like way. The storage vessel cannot be made of anything that exists in the physical world in the conventional sense, because anything that exists in the conventional sense is matter, and matter and antimatter annihilate. This is not a contamination problem that can be solved by making the container walls very pure or very smooth. It is a categorical incompatibility between the fuel and any conceivable physical container. The solution physics offers is the electromagnetic field. Charged antiparticles, specifically antiprotons and positrons, respond to electric and magnetic fields exactly as their normal matter counterparts do, but with reversed signs. A positive electric field that would attract an electron will repel a positron. A magnetic field that would curve a proton's path clockwise will curve an antiproton's path counterclockwise. This means that carefully shaped electric and magnetic fields can be used to suspend charged antiparticles in the center of an empty space, holding them away from all physical surfaces in a configuration where no matter touches the antimatter at all. The device that accomplishes this is called a penning trap. A penning trap uses a combination of a strong, uniform magnetic field and a shaped electrostatic potential well to confine charged particles in 3 dimensions. The magnetic field forces the charged particles to travel in tight circles around the field lines, preventing them from drifting sideways. The electrostatic potential well prevents them from escaping along the direction of the magnetic field. The particles orbit continuously in the center of the trap, never touching any solid surface, held in place by the combined action of the electromagnetic fields as long as those fields remain powered and stable. Penning traps work. They have been demonstrated to hold antiprotons for measurable periods of time. Experiments at CERN, specifically the BASE experiment, the baryon-antibaryon symmetry experiment, have demonstrated the storage of antiproton clouds in penning traps for periods of more than 1 year. This is a genuine and extraordinary experimental achievement. The antiprotons were held continuously by electromagnetic fields for over a year without annihilating. The BASE collaboration achieved this using a trap cooled to approximately 4 Kelvin, just 4 degrees above absolute zero, operating in a vacuum so hard that the residual gas pressure was negligible. In 2018, BASE also demonstrated something with direct implications for space applications: the successful transport of a small antiproton cloud from one location to another in a transportable penning trap. The device was called BASE STEP for Synchrotron and Transportable Experiment for Precision Measurements, and it represented the first time that antiprotons had been transported in a portable confinement device. The antiproton cloud survived the transport without annihilating. The number of antiprotons transported was tiny, a few hundred, but the principle of portable antiproton storage was demonstrated. The Alpha collaboration at CERN, the anti-hydrogen laser physics apparatus, works with a more complex form of antimatter, anti-hydrogen atoms, which are electrically neutral. An anti-hydrogen atom consists of a single antiproton orbited by a single positron. Because the overall atom is electrically neutral, it cannot be confined by electric fields the way charged antiprotons can. A penning trap does not work for neutral anti-hydrogen. Instead, the Alpha team uses a magnetic trap that exploits a more subtle effect. Anti-hydrogen atoms in their ground state have a small magnetic moment, meaning they are very weakly attracted to regions of low magnetic field. A carefully shaped magnetic field with a local minimum in the center can trap neutral anti-hydrogen atoms in that minimum, provided the atoms are cold enough that their thermal energy does not exceed the depth of the magnetic potential well. The depth of this magnetic trap for neutral anti-hydrogen atoms is approximately equivalent to 0.5 degree Kelvin in energy terms. This means the anti-hydrogen atoms must be cooled to temperatures well below 1 Kelvin to be trapped and held. Any anti-hydrogen atom with even a tiny amount of thermal energy above the trap depth will escape the magnetic minimum and strike the wall of the apparatus, annihilating immediately. The trap is extraordinarily shallow by any engineering standard. Holding antimatter in it is like trying to keep water in a bowl with sides 1 millimeter high on a table that vibrates. The breakthrough of November 2025, achieved by the Alpha collaboration with leading contributions from physicists at Swansea University and published in Nature Communications, addressed precisely this constraint. The technique used laser-cooled beryllium ions as an intermediary cooling agent. Here is how it worked. Beryllium ions, which are normal matter particles and therefore easy to manipulate with lasers, were loaded into the same trap region as the positrons that would eventually be combined with antiprotons to form antihydrogen. Laser cooling of the beryllium ions, using precisely tuned laser beams that extract kinetic energy from the ions through photon absorption and emission, brought the beryllium ion cloud down to temperatures below 10 Kelvin. The laser-cooled beryllium ions then exchanged energy with the surrounding positron cloud through electromagnetic interactions, cooling the positrons sympathetically, meaning through thermal contact rather than direct laser interaction, to temperatures below 10 Kelvin as well. This was colder than the previous threshold of approximately 15 Kelvin that the Alpha team had been able to achieve through other cooling methods. Colder positrons make dramatically better antihydrogen. The antihydrogen atoms formed when cold positrons combine with antiprotons inherit the thermal properties of the positrons. Cold positrons produce cold antihydrogen. Cold antihydrogen is far more likely to have thermal energy below the half Kelvin trap depth, meaning far more of the produced antihydrogen atoms can actually be trapped and held rather than immediately escaping and annihilating. The result was dramatic. The new technique enabled the trapping of a record 15,000 antihydrogen atoms in under 7 hours. Previous methods had required 10 weeks to accumulate 16,000 antihydrogen atoms for a precision spectroscopy experiment. In the full 2023 to 2024 experimental runs, using the beryllium-assisted cooling technique, the Alpha collaboration produced more than 2 million antihydrogen atoms in total. 2 million atoms. That number, compared to the 10 nanograms of antiprotons produced annually by CERN's full infrastructure, represents an improvement not in the total mass of antimatter created, but in the efficiency and rate at which antihydrogen can be formed and trapped, which is what enables the precision measurements that are the collaboration's primary scientific goal. In 2025, the collaboration was actively using this unprecedented supply of antihydrogen to study the effect of gravity on antimatter atoms with greater precision than ever before. The gravity experiment connects to a question that had profound implications for all antimatter research and for certain speculative propulsion proposals. For decades, some theorists had proposed that antimatter might fall upward in a gravitational field rather than downward. If antimatter had negative gravitational mass, it would be gravitationally repelled by normal matter rather than attracted to it. This speculative property, sometimes called anti-gravity, would have extraordinary implications. Among other things, it would mean that a mixture of matter and antimatter might act as a gravitational dipole, potentially enabling exotic propulsion concepts based on gravitational repulsion rather than momentum exchange. The 2023 result from the Alpha G experiment. The Alpha collaboration's dedicated gravity measurement apparatus settled this question definitively at the level of precision achievable in that run. When antihydrogen atoms were allowed to fall freely inside a vertical tube, with the magnetic trap gradually switched off, roughly 80% of the atoms fell downward and escaped through the bottom of the apparatus, while approximately 20% escaped through the top. The asymmetry between downward and upward escape matched the prediction for antihydrogen falling toward Earth under normal gravitational attraction, with essentially the same gravitational acceleration as normal hydrogen. The measurement precision was approximately 20%, meaning the gravitational acceleration of antihydrogen was confirmed to be downward and consistent with normal gravitational attraction to within that precision. This result, reproduced in the 2024 experimental run and published with the additional precision that the larger antihydrogen sample enabled, rules out the possibility that antimatter falls upward. Antihydrogen falls down. Antimatter is gravitationally attracted to the Earth, not repelled. The gravitational mass of antimatter is positive, not negative. Antigravity as a propulsion shortcut does not exist, at least not in the form that relies on antihydrogen being gravitationally repelled by Earth. This result matters for the production and containment story in a specific way. It removes from the table one category of speculative containment approach that had occasionally been discussed. If antimatter had negative gravitational mass, it might be possible in principle to use gravitational levitation in deep space, where other gravitational sources could be arranged to hold antimatter suspended. The confirmed positive gravitational mass of antihydrogen means that any containment solution must be purely electromagnetic, exactly as Penning traps and magnetic traps currently provide. There is no gravitational trick available. The engineering must proceed through electromagnetic confinement alone. The current laboratory record for antiproton storage in a Penning trap is remarkable, but the gap between laboratory achievement and spacecraft application is itself a kind of engineering chasm. Laboratory Penning traps are large, fragile, power-hungry devices that require superconducting magnets cooled to liquid helium temperatures, ultra-high vacuum systems that would require careful isolation from any vibration or thermal disturbance, and continuous monitoring and field adjustment systems to maintain the confinement. The base step portable trap demonstration showed that transport of antiprotons in a confined state is possible in principle, but the device weighed hundreds of kilograms and required its own cryogenic support infrastructure. Scaling a Penning trap from holding a few hundred antiprotons in a laboratory to holding micrograms of antiprotons in a spacecraft-grade device is not simply a matter of making the trap bigger. The number of antiprotons in 1 microgram is approximately 6 times 10 to the 17th 600 quadrillion individual particles. A laboratory Penning trap currently holds on the order of thousands to millions of particles. The gap between millions and 600 quadrillion is a factor of approximately 100 billion. The electromagnetic fields required to confine that many particles without the space charge of the cloud itself, destabilizing the confinement present. Plasma physics challenges that are qualitatively different from the challenges of confining small, well-controlled clouds. Proposed designs for spacecraft-grade antimatter storage tanks have been studied by researchers, including those at the Pennsylvania State University, in collaboration with NASA, and they converge on configurations using superconducting magnetic coils, generating field strengths of several Tesla, arranged in trap geometries that can hold macroscopic quantities of antiprotons in a kind of non-neutral plasma state, where the electromagnetic forces balance the mutual Coulomb repulsion of the stored antiprotons. These designs remain entirely theoretical. No device approaching this capability has been built or tested, but the theoretical framework is grounded in plasma physics and electromagnetic engineering that is understood well enough to make credible estimates of what would be required. The containment time is also a critical parameter. An antiproton stored in a perfect electromagnetic trap will eventually be lost, not through annihilation with normal matter, because it never touches any, but through collisions with residual gas molecules in the imperfect vacuum and through interactions with electromagnetic noise that perturb its orbit until it drifts into the trap wall. The base experiment's 1-year storage demonstration was achieved in conditions of extraordinary vacuum and electromagnetic isolation. In a functioning spacecraft operating in the real space environment, maintaining those conditions over the years-long duration of an interstellar mission represents an additional layer of engineering challenge. There is also the question of what happens when something goes wrong. An antimatter storage failure on a spacecraft is not like a fuel tank leak. A leak of antiprotons from their electromagnetic confinement means the antiprotons immediately begin annihilating with whatever normal matter they encounter. The inner walls of the containment structure, surrounding spacecraft components, anything in the vicinity. The energy released per annihilation event is modest for a single particle, but a storage failure, releasing a significant fraction of a microgram of antiprotons, would deposit enormous energy in the spacecraft structure in a very short time. Engineering. The fail-safe systems for an antimatter storage device requires thinking carefully about every mode of confinement, failure, and ensuring that any release of antimatter is directed away from critical systems or is terminated fast enough to limit the damage. These are genuine engineering problems with serious technical content. They are not obstacles that make antimatter propulsion impossible in principle. They are obstacles that require sustained, funded, organized engineering effort over timescales that are currently difficult to predict with confidence. The momentum in the field is real. CERN's breakthroughs between 2023 and 2025 represent genuine progress, not incremental shuffling. The factor of 10 improvement in anti-hydrogen trapping efficiency achieved through beryllium-assisted cooling is the kind of advance that changes the practical scope of what experiments can be done, and the trajectory of improvements over the past 2 decades in anti-hydrogen trapping, laser manipulation, spectroscopy precision, and gravity measurement has been consistently upward. But even as the laboratory science accelerates, the gap between 15,000 trapped anti-hydrogen atoms and the grams of antimatter that an interstellar engine requires remains vast enough to ensure that the engine remains in the future rather than in the present. The question of how to close that gap leads directly into a mystery that sits not in engineering, but in cosmology, in the story of where antimatter came from and why there is so little of it left. Because the answer to the production crisis may ultimately depend on understanding not how to make more antimatter in accelerators, but why the universe made so little of it in the first place. There is a question buried beneath the engineering of antimatter propulsion that most discussions of the subject never reach, because most discussions stop at the level of production costs and containment physics and particle accelerator output figures. Those are real problems with real numbers attached to them, and they deserve the attention they receive. But they are, in a certain sense, proxies for a much deeper problem, one that is not about engineering at all, but about the fundamental structure of the universe and the specific conditions of its birth. The question is this: where did all the antimatter go? The Big Bang, the origin event of the observable universe, approximately 13.8 billion years ago, did not create matter alone. The physics of the early universe, the particle physics that governed the first fractions of a second of cosmic time, when temperatures were incomprehensibly high and energies were orders of magnitude beyond anything achievable in modern particle accelerators, was symmetric. The processes that produced particles also produced antiparticles. The same mechanisms that create proton-antiproton pairs in CERN's target collisions operated throughout the entire volume of the early universe, simultaneously, everywhere, continuously, for the first tiny fraction of a second of time. Every proton created was accompanied by an antiproton. Every electron was accompanied by a positron. Every quark was accompanied by an antiquark. The universe began, in terms of fundamental particle content, with equal amounts of matter, and antimatter. This is not speculation or a theoretical preference. It is a direct consequence of the CPT symmetry theorem that was discussed in Part 1, which states that the laws of physics are invariant under the simultaneous reversal of charge, parity, and time. CPT symmetry requires that every physical process produces matter and antimatter in identical amounts. If the laws of physics are CPT symmetric, and they are CPT symmetry is among the most precisely experimentally tested principles in all of physics, then the early universe's particle production processes must have been matter-antimatter symmetric, equal amounts of both. If equal amounts of matter and antimatter were created, and if they behaved identically under every physical law, then the subsequent evolution of the universe should have proceeded symmetrically. Matter and antimatter should have annihilated with each other as the universe cooled, eliminating both in equal measure, and the end state should have been a universe containing no matter and no antimatter at all, only the gamma-ray photons produced by the final annihilations, spreading out forever through an expanding empty space. That is not the universe we live in. The universe we live in contains matter everywhere and antimatter almost nowhere. Every atom in your body is matter. Every atom in every star, every planet, every gas cloud, in every galaxy is matter. The observable universe, across its full extent of approximately 93 billion light-years in diameter, is made of matter. The antimatter that should have been present in equal quantity is gone. Physicists call this the matter-antimatter asymmetry problem, or the baryogenesis problem. Baryon refers to the class of particles that includes protons and neutrons, the components of atomic nuclei, and baryogenesis refers to the process by which an excess of baryons over antibaryons was produced in the early universe. The asymmetry between baryons and antibaryons in the observable universe is approximately 1 part in 10 billion. For every 10 billion antiprotons that existed in the early universe, there were 10 billion and 1 protons. The 10 billion antiprotons and 10 billion of the 10 billion and 1 protons annihilated with each other, leaving the 1 extra proton behind per 10 billion of everything. That 1 extra proton per 10 billion is everything. Every star, every galaxy, every living thing, every atom of every planet. All the matter in the observable universe is the residue from that asymmetry of 1 part in 10 billion. The asymmetry is real. It is measured. It is one of the most precisely established facts in observational cosmology. Cosmic ray observations, measurements of the cosmic microwave background radiation, the large-scale structure of the observable universe, all confirm unambiguously that the observable cosmos is matter-dominated and contains essentially no primordial antimatter. The question of why is entirely unanswered in any complete, experimentally confirmed sense. In 1967, the Soviet physicist Andrei Sakharov identified the 3 conditions that any physical process generating a matter-antimatter asymmetry must satisfy. These conditions, now called the Sakharov conditions, are widely cited and worth understanding precisely because they define the shape of the problem. The first Sakharov condition requires baryon number violation, the existence of physical processes that do not conserve the total number of baryons minus antibaryons. In ordinary physics, as currently understood, the total baryon number is conserved in every interaction. You cannot create a proton without also creating an antiproton, or destroy a proton without destroying an antibaryon with it. If baryon number is always conserved, There is no way to start from a baryon-symmetric universe and end up with more baryons than antibaryons. Some process must exist that violates baryon number conservation. The standard model of particle physics, the theoretical framework that successfully describes all known fundamental particles and their interactions, does contain a mechanism for baryon number violation at extremely high temperatures and energies through a process called Sphaleron transitions. Electroweak baryogenesis processes mediated by the topology of the electroweak gauge fields. These processes were theoretically active in the early universe at temperatures above approximately 10 to the 15th Kelvin and could in principle generate a baryon asymmetry. However, calculations of how much asymmetry they actually generate within the standard model framework fall far short of the observed 1 part in 10 billion asymmetry of the universe. The standard model has baryon number violation, but not enough. The second Sakharov condition requires C and CP symmetry violation, the violation of the symmetry between particles and antiparticles, and the combined symmetry of charge conjugation and parity transformation. If particles and antiparticles behaved identically in every respect under every physical law, any process that created an excess of baryons would be exactly mirrored by an equally probable process creating an excess of antibaryons, and no net asymmetry would result. Some difference between the behavior of matter and antimatter must exist to allow one to dominate over the other. CP symmetry violation has been observed experimentally. It was first discovered in 1964 by James Cronin and Val Fitch in the decay of particles called kaons, a discovery for which they were awarded the Nobel Prize in Physics in 1980. CP violation has since been observed in the decays of B mesons and D mesons in experiments at the Stanford Linear Accelerator Center at Bell in Japan and at LHCb at CERN. These observations confirm that CP symmetry is not exact in nature. Matter and antimatter do not behave in precisely identical ways in certain decay processes. But the amount of CP violation so far observed in particle physics experiments is again far too small to account for the observed matter-antimatter asymmetry of the universe. The standard model predicts a specific level of CP violation in kaon and B meson decays, and observations are consistent with those predictions. But extrapolating the observed CP violation to the early universe generates a matter asymmetry, many orders of magnitude smaller than what is actually observed. Something is missing. Either there are additional sources of CP violation beyond those captured in the standard model, or the mechanism of baryogenesis operates through physics not yet experimentally discovered. The third Sakharov condition requires departure from thermal equilibrium in the early universe. If all processes were in perfect thermal equilibrium, meaning every reaction proceeded at exactly the same rate as its reverse, then any asymmetry generated by a CP violating process would be immediately washed out by the reverse process. Some epoch of non-equilibrium conditions must have existed during which a net asymmetry could accumulate and survive. The expanding universe naturally provides departures from equilibrium as it cools, and certain proposed baryogenesis mechanisms exploit phase transitions in the early universe's field content as a source of non-equilibrium conditions. All three Sakharov conditions can in principle be satisfied, and theoretical physicists have proposed numerous specific baryogenesis mechanisms that satisfy them, including electroweak baryogenesis, leptogenesis, aphlekdyne baryogenesis, and others. But none of these mechanisms has been experimentally confirmed, The actual process by which the universe generated its matter-antimatter asymmetry remains unknown. It happened in the first fractions of a second after the Big Bang, at energies that particle accelerators cannot currently reach and may never be able to reach directly. The evidence it left behind is the universe itself, observable but not directly reversible. The Alpha Collaboration's precision spectroscopy measurements of antihydrogen are directly relevant to this search. The 1s2s transition frequency in hydrogen, the frequency of light emitted when an electron jumps between two specific energy levels, has been measured in normal hydrogen with extraordinary precision to approximately 15 significant figures. The same transition in antihydrogen has been measured with increasing precision over successive alpha experimental runs. If any difference existed between the transition frequency in hydrogen and the transition frequency in antihydrogen, even a difference at the 14th decimal place, it would indicate a violation of CPT symmetry, the foundational theorem that requires matter and antimatter to be perfect mirror images of each other in all properties. CPT violation would be revolutionary. It would break one of the deepest symmetry principles in theoretical physics, requiring a fundamental restructuring of quantum field theory. More importantly, for the baryogenesis question, it would provide a source of asymmetry between matter and antimatter that goes beyond the CP violation already observed in meson decays, potentially large enough to account for the cosmological asymmetry. The alpha spectroscopy measurements are, at their core, a search for CPT violation, a search for a crack in the mirror between matter and antimatter that might explain why one won over the other. As of the most recent alpha measurements, no difference between hydrogen and antihydrogen spectroscopy has been detected within the current measurement precision. CPT symmetry holds, at least to the level that the current experiments can probe. But each new generation of measurements, enabled by the larger antihydrogen samples that the beryllium-assisted cooling technique now provides, reaches deeper levels of precision. The absence of a detected difference is itself a result of scientific value, placing upper limits on the possible magnitude of CPT violation. And the search continues, because the question it is asking is arguably the most profound question in all of physics. Here is what that means. When placed alongside the propulsion problem, the scarcity of antimatter that makes engine design so brutally difficult is not an accident of geography or a coincidence of cosmic timing. It is the direct and specific consequence of whatever process caused matter to dominate over antimatter in the early universe. The fact that CERN can produce only 10 nanograms of antiprotons per year, that a gram of antimatter costs tens of trillions of dollars, that the nearest natural source of antimatter in meaningful quantity might be the Van Allen belts, where cosmic rays produce a faint drizzle of antiprotons. All of this is a direct reflection of the 1 in 10 billion asymmetry that emerged in the first fraction of a second of cosmic time. The universe is not indifferent to whether humanity can build an interstellar engine. The universe does not care about that. But the universe is, in a deep and specific sense, the reason the engine is so hard to fuel. The same physical process that allowed matter to survive the Big Bang, that allowed hydrogen and helium to form, that allowed stars to ignite and produce heavy elements, that allowed planets to form around those stars, that allowed chemistry to produce life, and that allowed that life to develop brains capable of reasoning about physics. That same process is the reason antimatter is so vanishingly rare and so extraordinarily difficult to produce. The existence of everything depends on the scarcity of the perfect fuel. This is not a poetic observation. It is a physical statement with specific content. If the matter-antimatter asymmetry had been zero, if the universe had been perfectly symmetric, then all matter and all antimatter would have annihilated in the first seconds of cosmic time, leaving nothing but photons, expanding forever through an empty universe. No atoms, no stars, no planets, no life, no physicists measuring antihydrogen transition frequencies. The asymmetry of 1 part in 10 billion, which left behind a trace of matter that became everything, simultaneously left behind a universe almost entirely devoid of antimatter. The abundance that enabled us to exist is inseparable from the scarcity that makes the most powerful engine conceivable almost impossible to fuel. There is a second layer to this relationship that deserves its own careful statement. It involves what solving the antimatter production problem would actually require, not in engineering terms, but in physics terms. To produce antimatter efficiently at scale, to reduce the cost from trillions of dollars per gram to something practically achievable, would require either dramatically improved accelerator technology, a natural source of antimatter, or a fundamentally new physical process for creating antimatter that does not exist within the current standard model. Each of these paths leads through the matter-antimatter asymmetry problem in a specific way. Dramatically improved accelerator efficiency would require understanding and optimizing the quantum field theory processes by which antiprotons are produced in collisions. Those processes are governed by the strong nuclear force and quantum chromodynamics, the theory of quarks and gluons. Deeper understanding of those processes might reveal production pathways that are more efficient under specific conditions. But the hard thermodynamic flaw that you must invest at least as much energy as the rest mass of the pair you are creating cannot be circumvented. Efficiency improvements reduce overhead waste, but they cannot eliminate the fundamental energy cost. A natural source of antimatter that could be harvested without accelerator production would likely require a region of space where baryogenesis proceeded differently than in our local observable universe, producing antimatter-dominated regions that survived to the present day. Such regions, sometimes called antimatter domains, have been proposed theoretically, but observational evidence places very tight constraints on how large and how abundant they could be. The gamma-ray emissions from the boundaries between matter and antimatter domains, where annihilation would continuously occur, have been searched for extensively and not found at levels that would indicate large nearby antimatter domains. The observable universe is matter-dominated as far as our observations currently reach. A fundamentally new physical process for creating antimatter, one that operates at lower energy costs or higher efficiency than proton collision methods, would require physics beyond the standard model. But here is the recursive depth of the situation. Physics beyond the standard model is precisely what is needed to explain baryogenesis. The same theoretical framework that would explain why matter won over antimatter in the early universe might also reveal new particle physics processes that enable more efficient antimatter production. Solving the mystery of the matter-antimatter asymmetry and solving the antimatter production problem for propulsion are not separate projects. They may be the same project, approached from different directions. This convergence gives the search for baryogenesis its propulsion significance. Every alpha measurement of antihydrogen spectroscopy, every base measurement of the antiproton magnetic moment. Every search for CP violation in B meson and D meson decays at particle colliders. Every theoretical proposal for physics beyond the standard model, motivated by the baryogenesis puzzle, all of it is simultaneously science, aimed at understanding the origin of the observable universe, and science whose eventual fruits might enable the manufacture of the fuel needed to leave the solar system. The antimatter engine and the origin of the universe are not adjacent topics that happen to share the word antimatter. They are deeply entangled. The engine requires understanding why the universe made matter dominant. Understanding why the universe made matter dominant requires the kind of physics that would transform antimatter production. The scientific program pointed at the stars, and the scientific program pointed at the Big Bang converge on the same experimental frontier. There is something else worth naming here, something that belongs specifically to the philosophical territory that this final part of the story is equipped to explore. Human beings have been looking at the night sky for as long as there have been human beings. Every civilization in recorded history has looked at the stars and wondered what they are and whether they can be reached. The distances involved have always been understood, in rough terms, to be enormous beyond easy comprehension. The impulse toward the stars has always lived in tension with the practical reality that reaching them seems impossible with any tool currently in hand. Antimatter propulsion does not eliminate that tension. It transforms it. It transforms it from a permanent impossibility into a specific and solvable, if extraordinarily difficult, engineering and physics problem. The stars are not unreachable in principle. They are unreachable with current tools. The gap is real, but the gap has a specific physical character. It is precisely defined by the matter-antimatter asymmetry that pervades the observable universe, and by the production and containment challenges that asymmetry creates. Every human civilization that has ever dreamed of reaching another star has been separated from that goal by a barrier rooted, ultimately, in a process that occurred in the first microseconds of the universe's existence. The Big Bang's asymmetry echoes across 13.8 billion years of cosmic time and shows up as the price tag on a gram of antiprotons. The connection is not metaphorical, it is causal. The physics of the first microsecond of time determines the difficulty of building an interstellar engine in the 21st century. There is a specific texture to the universe's relationship with antimatter that the full arc of this story reveals. The universe created the perfect fuel. It created it in quantities equal to all the matter that exists in the observable cosmos, in the first fraction of a second of time. Then, through a process still not fully understood, it nearly eliminated all of it, leaving behind a trace so small that humanity has spent decades learning to count atoms of it. And it left the evidence of that elimination encoded in the structure of particle physics, in the small differences between matter and antimatter that show up in kaon decays and meson oscillations and transition frequencies of hydrogen and antihydrogen, daring us to find and decipher it. The universe hid the perfect fuel. It hid it in a way that requires solving one of the deepest problems in theoretical physics to recover. And in doing so, it guaranteed that any civilization capable of building an antimatter engine would first have to become a civilization capable of understanding its own cosmic origin, capable of answering why the universe contains matter rather than nothing, why the specific asymmetry of 1 in 10 billion emerged from conditions of extreme symmetry, and what physical law broke that symmetry in the direction that made everything possible. This is not a comfortable thought in the sense of providing reassurance that the engineering will be easy or that the timelines are short. It is a clarifying thought. It places the antimatter engine where it belongs, not as a technology waiting to be built once someone finds the funding, but as a marker of what it means to be a civilization that truly understands the universe it inhabits. The drawings exist. The physics is real. The numbers are verified. The energy is there, embedded in the annihilation of matter and antimatter, available to any civilization that can navigate the same mystery that defines the structure of the cosmos. CERN trapped 15,000 anti-hydrogen atoms in 7 hours in November of 2025. That is a fact. It represents a 10-fold improvement in efficiency. The Alpha collaboration is using unprecedented anti-hydrogen supplies to measure how antimatter falls under gravity with increasing precision, reaching toward the level where any deviation from CPT symmetry would become visible, where the crack in the mirror between matter and antimatter might finally show itself. The trajectory is upward. The momentum is real. The distance between 15,000 atoms and a gram of fuel is immense. But 15,000 atoms is more than 10,000 atoms, and 10,000 was more than 1,000, and 1,000 was more than 10. Every improvement in trapping efficiency, every new cooling technique, every additional year of precision spectroscopy is a step taken along a path that physics has confirmed leads somewhere real. The engine at the end of that path could carry human beings to another star within a single lifetime. That is not a dream in the vague sense of something longed for but never approached. It is a dream in the specific sense of a destination with a verified route, one whose challenges are genuinely immense, whose timelines are genuinely uncertain, and whose rewards are genuinely beyond anything else humanity has ever contemplated building. The universe made the perfect engine and then hid it inside the deepest question in all of physics. And the answer to that question is also the answer to why we are here. Why the night sky contains stars rather than nothing. Why atoms exist, and chemistry is possible, and life emerged, and minds developed, capable of holding all of this in awareness simultaneously. We are looking for the fuel. We are also, whether we realize it or not, looking for ourselves. Sail softly into the dark. Dreamer, the stars are patient, and so are you.